Good morning to all of you. This is lecture number 10. In this lecture, we will discuss about the shear force in beam. What is shear stress in beam? In the last previous lecture, we have seen that when a part of a beam is subjected to a constant bending moment and zero shear force, then there will be only bending stress in the beam. The shear force will be zero as the shear stress is equal to shear force divided by the area. As shear force is zero, the shear stress will be zero. But in actual practice, a beam is subjected to a bending moment which varies from section to section. Also, the shear force acting on the beam is not zero. It also varies from section to section. Due to this shear force, the beam will be subjected to shear stresses. These shear stresses will be acting across transverse section of the beam. These transverse shear stresses will produce complementary horizontal shear stresses which will be acting on longitudinal layers of the beam. Hence, the beam will also be subjected to the shear stresses. In this lecture, the distribution of shear stresses across the various cross section, that is rectangular, circular, I section, T section, will be discussed. This is a simple diagram of a rectangular section which shows a simply supported beam or carries a uniformly distributed load for a uniformly distributed diagram. The shear force and bending moment will vary along the length of the beam. Consider the section of AB and CD of the beam at a distance dx apart. Let at the section AB, F is the shear force, M is the bending moment, and CD is equal to F plus dF is equal to shear force, M plus dM is equal to bending moment, I is equal to moment of inertia. Let it is required to find the shear stresses on the section AB at a distance y1 from the neutral axis. Show the cross section of the beam. On the cross section of the beam, the EF at the line at a distance y1 from the neutral axis. Now consider the part of the beam also, the level EF and between the section AB and CD. This part of the beam may be taken to consist of an infinite numbers of elements cylinders such as areas dA and length dx. Consider one such element cylindrical at a distance dy from the neutral axis. Let us suppose dA is equal to area of the elementary cylinder, dx is equal to length of the elementary cylinder, y is equal to distance of the elemental cylinder from the neutral axis, sigma is equal to intensity of bending stresses on the end of the elemental cylinder of the section AB. Let assume sigma plus d sigma is equal to intensity of the bending stresses on the end of the elementary cylindrical on the section CD. The bending stress at the section y from the neutral axis is given by the equation 7.6 as m by I is equal to sigma by y is equal to E by R. That's why sigma is equal to mi multiplied by y. For a given beam, the bending stress is a function of bending moment and the distance y from the neutral axis. Let us find the bending stresses on the end of the elementary stresses at the section AB and also the section CD. Bending stresses on the end of the elementary cylinder of the section AB, that is sigma is equal to m by I multiplied by y. I multiplied by y multiplied by dA. Similarly, the forces on the end of the elementary cylinder on the section CD, that is sigma plus d sigma multiplied by dA, it is equal to m plus dm divided by I multiplied by y plus dA. At the two ends of the elemental cylinder, the forces are different. They are acting along the same line but are in opposite direction. Hence, there will be an unbalanced force on the elementary cylinder. Net unbalanced force on the elementary cylinder is equal to m plus dm divided by I multiplied by y multiplied by dA minus m upon I multiplied by y dA. On solving this equation, we get dm by I multiplied by y multiplied by dA. The total unbalanced force along the level EF and between the section C and AB and CD may be found out by considering all the elemental cylinder between the section AB and CD and above the level EF. Then total unbalanced force, that is m by I multiplied by y dA. Integrating this equation, we get m by I multiplied by A multiplied by y bar, where y bar is equal to distance of the CG of the area A from the neutral axis and m is equal to bending moment. So therefore, the shear stress at any level EF, that is the total unbalanced force, should be equal to Tm multiplied by A y bar divided by I. Let us assume tau is equal to intensity of the shear, horizontal shear at the level EF. B is equal to width of the beam at the level EF. area on which tau is acting, that is B dx, and shear force due to tau is equal to shear stresses multiplied by shear area. It is equal to tau multiplied by B dx. So equating the two values of the shear force given by the equation 2 and 3, we get tau B dx is equal to dm divided by I multiplied by a y bar. So y bar is the distance from the neutral axis. So tau is equal to dm divided by I multiplied by a y bar divided by I into b. So next is the shear stresses distribution for different sections. The following are the important section over which the shear stresses distribution is to be obtained. Number 1, rectangular section, circular section, I section, T section, and miscellaneous sections. In case of rectangular section, previous figure 8 point show rectangular section of a beam with width of B, depth of D. Let F is the shear force acting on the section. Consider label EF at a distance y from the neutral axis. The shear stress at this level is given by tau is equal to FAY divided by B into y. So A is equal to area of the section above, shaded area D by 2 minus y multiplied by diagram. Y is equal to distance of the CG A from the neutral axis, that is y plus 1 by 2 d by 2 minus y, and it is equal to 1 by 2 y plus d by 2, where B is equal to the actual width of the section at level EF, I is equal to moment of inertia. Substituting these values in the following equation, we get tau is equal to F divided by Qi multiplied by d square divided by 4 minus y square. From equation 8.2, we see that the tau increases as y increases. Also, the variation of tau with respect to y is a parabolic, and at top put y is equal to d by 2 and tau is equal to 0. Next is at neutral axis y is equal to 0, hence tau is equal to 1.5 F divided by BD. Now average shear stress, that is tau average, is equal to shear force divided by area of the section, which is equal to F divided by B into D. Substituting the above value in the equation 1, we get tau is equal to 1.5 multiplied by tau average. From equation 8.3, it gives the shear stresses at the neutral axis where y is equal to 0. This stresses is also the maximum value, that is tau max is equal to 1.5 multiplied by tau average. From the equation 8.1, tau is equal to a y bar divided by I into b. In this equation, the value of a y bar can also be calculated as given below. A y bar is equal to moment of shaded area and d is equal to elementary area strip. Is the moment of shaded area about the neutral axis, that is integration of y to d by 2 multiplied by y d into dy. B multiplied by integration of y to d by 2 multiplied by y dy. On solving this equation, we get tau is equal to f by 2y d square by 4 minus y square. This is the parabolic equation in nature. So in this lecture, we will discuss. We have covered shear stresses in a rectangular beam and circular beam. In the next lecture, we will discuss about the problem which is related to shear stresses in beam. So thank you.